Hello and welcome back. Today we'll be completing question 8 from the 1998 step 3. This is a question involving spheres, lines, planes and 3D vectors. Let's get started. Question 8, part 1. Show that the line vector r equals vector b plus lambda vector m, where m is a unit vector, intersects the sphere vector r dot vector r equals a squared at 2 points if a squared is greater than vector b dot vector b minus vector b dot vector m squared. Write down the corresponding condition for there to be precisely one point of intersection. If this point has position vector p, show that vector m dot vector p equals 0. Part 2. Now consider a second sphere of radius a and a plane perpendicular to a unit vector n. The centre of the sphere has position vector d, and the minimum distance from the origin to the plane is L. What is the condition for the plane to be tangential to this second sphere? Part 3. Show that the first and second spheres intersect at right angles, i.e. the two radii to each point of intersection are perpendicular, if vector d dot vector d equals 2a squared. Pause the video to have a think, and once you're ready, restart to see if you were correct. Let's get started. Part 1. So, firstly, consider this diagram on the left. This here is to find the closest distance c between the line and the origin. Firstly, we'll notice that the size of vector b, all squared, is equal to vector b dot vector b. We'll also notice that k is vector b dot vector m. By Pythagoras' theorem, we have c squared equals the size of vector b squared minus k squared, which is vector b dot vector b minus vector b dot vector m squared. Now, for two intersections, we need a greater than c greater than 0. So a squared is greater than c squared, which is vector b dot vector b minus vector b dot vector m squared, as required. If there is to be only one intersection, then we need a equals c, so a squared is equal to the c squared from above. As this point is the only point of contact, then the line will be a tangent to a great circle of the sphere, meaning that p, which lies along a radius, is perpendicular to m, the direction of the line. Thus, we have vector m dot vector p equals 0, as required. Now, let's move on to part 2. Firstly, we will have a very good look at the diagram. Here, we have a sphere at centre d with position vector d, and with radius a. Plane alpha is tangent to this sphere at point A. Plane alpha also has vector n as its normal vector. Notice that L is the minimum distance between the origin and the plane alpha. In the diagram, we have LA is parallel to XD. We also have OL is parallel to DA, which is parallel to vector n, all of which are perpendicular to plane alpha. We thus have L is equal to B plus A, as marked on the diagram, and so L is equal to A plus vector D dot vector n. Now let's move on to part 3. Here we have two cones meeting. This, of course, is the area where two spheres of radius a and separation d are intersecting. The size of vector d is equal to root 2 of a, as shown on the right. Therefore, we can draw a triangle with longest side root 2 of a and shorter sides a. Thus, by the converse of Pythagoras' theorem, the angle between the two radii to a point of intersection will be a right angle, as a squared plus a squared is 2a squared. And that's our answer. If you liked our video, please like and subscribe, and we'll see you next time for some more fun maths problems. Thanks for watching, and goodbye.